next talk in this session. Let's thank Professor Mednik and welcome Professor Ulrich Pinkall. Yeah, so Professor Pinkall, you are there, right? Professor Pinkall?
Yes, I'm here.
Yeah. Hello. Yeah.
So let me
you can share your screen.
Yes. Do you see it? Yes.
Yeah, Riemannian geometry in plasma physics.
Great.
That's the title of Professor Pinkall's lecture. And I see that Professor Pinkall is sitting in a room surrounded by many machines. So those are computational devices, or I mean, it's a lab.
That's not the real room, but it's a background.
Oh, okay. I thought you were sitting in a computational lab. I mean,
yeah, but it's a movie. You can see the screens blinking if you want. Yeah.
Oh, yeah. Okay. Mr. Pinkall, please, I mean, we welcome you to this conference. So Professor Pinkall will be speaking now on Riemannian geometry in plasma physics. Yeah. Over to you, Professor Pinkall.
Yeah, of course, I'm very honored to be here on the occasion of Ravi's 80th birthday. So it's really a pleasure even to see him well and alive here. And I met Ravi in 1985, I guess. That was in Bonn at the Max Planck Institute. And we together organized a special activity on conformal geometry. You see, that's a publication that came out of it. And so what is conformal geometry? So if we have a Riemannian manifold, and a metric, let's call it ds, and the function, then you can just change the metric by multiplying this or given metric by e to the u. So it's up to this factor, which is a function, it's still the old metric. And in particular, if you start with a Euclidean metric, a flat metric, then this conformally changed metric would be called a conformally flat metric, because up to a conformal change, it's still a flat metric. Okay, and Ravi had done some work on conformal geometry and in really Riemannian geometry than before. And I want to give now some applications to physics. In recent years, I have been working on applications of differential geometry to somebody has to be muted, sorry.
Yeah, everyone please mute yourself. Devendra, can you mute? I mean, maybe Nova 9. So Nova 9, can you mute yourself, please?
Okay. Anyway, so I've been working on differential geometry to physics simulation.
Sorry for interruption. Devendra, mute others, please. Okay, Professor Pinkall, you can go ahead. There's too much noise. Yeah. Host can mute. So, Devendra, can you mute the noise? Nova 9, can you mute yourself? Nova 9. whoever is there. Hello.
I think the organizer can also mute
Yeah,
everyone.
I am not the co-host, so Professor
That's all right.
Kulkarni, can you ask Devendra to mute the noisy person, Nova 9? It can be done from your device. Yeah.
Yeah, okay. Do you still hear me? Yeah.
Yeah, I can see you. Now the noise is less, you can go ahead.
Yeah.
Yeah, let me make a phone call and ask one the technical person. Yeah.
Okay, so yeah, so that is a view of the sun, really, a few days photographs in October 2011, and you see there's a lot of going on. There's a lot of geometry. You see all these curves, yeah, and there's some motion, but basically it's a static thing. Yeah? And the task is, so how do you understand the shape of these structures, yeah, and how do you simulate them? Maybe if you have to simulate them for some purpose. Yeah? And so this is a closed up, in fact, and you see still the brightness changes a bit, yeah, but still it's a very static picture, yeah. And so what I want to come to is that these structures, yeah, they really are geodesics in such a conformally changed metric, yeah. And so this Riemannian, there's a certain not Euclidean metric, yeah, the Euclidean metric changed by a conformal vector near the sun. And if you know this metrics, then you can understand what's going on and also use it practically to simulate. Yeah. So that's the goal.
I think one knows one roughly knows the, hello?
Yeah, I hear you.
Yeah, one knows the atomic structure of the sun pretty well, I think.
Yes,
Just the helium or hydrogen. Please go ahead.
Yeah. So this is actually what you see is not really only gas; it's so-called plasma. So that is where the electrons and the protons are separated. Yeah, and it's really highly conducting, electrically conducting gas. Yeah, and there's a lot of magnetic field, and in fact, the structures you see follow the field lines of a magnetic field. So plasma is basically some gas, but highly, because it's so hot, it's electrically conducting, and then there's also a very strong electric or magnetic mostly influence. Yeah. Okay. Yeah. So what do we have to know? We can. There's this gas component. We have a gas pressure, which is a function on the manifold, yeah? And a magnetic field, which is a divergence-free vector field according to Maxwell's equation. Yeah? And then we have this magnetohydrostatic equation, which can be written like this. So nabla is a Levi-Civita connection, and the nabla BB, yeah, is a gradient of this total pressure, yeah, and this gas pressure plus something which is a magnetic pressure. Yeah. And you can already see, so if you think about the field lines, the integral curves of B, then if you take derivative in the direction of B, that's more or less like an acceleration. So this, you can see where geodesics might come into the picture. Okay, then there's a more, in situations like on the sun, there's also gravity involved. there's a gravitational potential, yeah, and you have then you have also gas density, yeah, mass density, which is a function, and then you get also this additional term in this magnetohydrostatics equation, which is minus rho gradient u, yeah. And so that's the equation we want to solve, yeah. And in fact, we want to look at special solutions to this equation, yeah. In fact, where there is more accessible geometry, that means we look at solutions where we have a decomposition of this manifold into domains M0 and some other domains M1 to Mk, and we just say there is no magnetic field, yeah, in this M0. So it's only gas, yeah, and also there is no gas at all. Yeah, it's vacuum inside of these magnetic domains. Yeah, and so we're looking at some discontinuous limiting case. Yeah, but we would still want solutions of these original equations, yeah, in the weak sense, sort of. Yeah, and so why is this realistic assumption? So the fact is that how these structures on the sun really arise is that you have some thin magnetic strands, yeah, filaments below the sun surface, yeah, and then because actually there are really the density is less inside of these strong magnetic field portions, and then they are lighter and they rise due to buoyancy, yeah, and so they rise above the sun surface, yeah, and expand further, and according to these equations of the whole dynamic equations, yeah, the gas which was in the thin filament, yeah, is still the same as in the filament above, yeah, and so it's really very thinned out. So in some limit we can say there's no gas at all in this arc, this solar loop above the surface. So, okay, so that is then the notation again. M0 is a gas domain, MB is where the magnetic field is, and this boundary of M. So M is really the exterior of the sun, and the boundary is the sun surface. Yeah. Okay, and yeah, so that's let's look at these equations now in this special case, yeah. And on M0, where there's no magnetic field, we just have that the gradient of this gas pressure is minus rho times the gradient of the gravity potential. And you see, if you have two functions whose gradients are proportional, then basically one function is a function of the other. And so let's under some mild topological assumptions, let's say the level sets of U are connected or something on M0. We have just one single gravitational pressure function, yeah, which is a function of the gravity potential, yeah, which is universal on the whole of M, not just on M0. Yeah. And so the gas pressure is really the restriction of this smooth function on the whole manifold. Yeah? And we treat this gravitational pressure as given on the whole space. So that's kind of, we don't have to, then we never will have to worry about gas and gas pressure anymore. That's just a given function on the whole manifold. Okay, so what is then the solution, the description? So we have this decomposition into these domains, yeah? And we have a vector field on this magnetic domain, divergence free, yeah? And yeah, and then it turns out, so these magnetic domains, they could also touch each other, yeah, but then one condition to be a weak solution is that the norm of the magnetic field is continuous across where these magnetic domains touch, yeah? And inside the magnetic domains, yeah, then this gas pressure term is gone. So we just have nabla BB is gradient of norm squared B half. Yeah? And so that will be, that's now a nice geometric equation, just vector field on Riemannian manifold. We will come to that. Yeah? And then also on the boundary of the magnetic domain, yeah, the norm squared half of the magnetic field has to be equal. This magnetic pressure has to be equal to the gas pressure outside. Yeah? So that's a boundary condition for norm B on the boundary of the magnetic domain. Yeah? That's how the gas comes into play. Yeah? So that's a quite simple geometric setup. Yeah? And
is the number K calculable or
no, it can be anything. It's just that we depends, of course, on the situation. Yeah? I will give examples right away. Yeah? Mm-hmm. And so let's look at this equation. Nabla BB is equal to the gradient here. And this really means that the field lines of B are geodesics of the metric, where you just rescale the given metric by norm B. Yeah? So inside of these magnetic domains, let's say it's non-zero. Yeah? And then, yeah, so these field lines really are geodesics, and that's what you have inside of these magnetic domains. Yeah? Okay, then now let's look at an example. Yeah, so let's say M is just free space, yeah, no gravity, and then with no gravity we have that that P is constant. Yeah, let's say P is 1/2. Yeah, and what you see here. That won't be a solution. Yeah, that won't be in equilibrium. That won't be a solution of these hydrostatics equations. Yeah, but this one would be. Yeah, so you have two interlinked tori. Yeah, and in fact, in this case, the tori touch, and you get a particular shape and a particular magnetic field inside. Which are indicated by these field lines. So that's, yeah. And so another way to visualize this magnetic field is by really filling the space by tubes. Yeah. And then where the field lines are less dense, yeah, the tubes are thicker. Yeah. So thick tubes mean weak magnetic field. Yeah? And you see one of the equations was that on the boundary, magnetic pressure equals gas pressure. And on the exterior, we have constant gas pressure. So that means on here now we have a constant magnetic field strength. That means constant thickness of these tubes on the boundary here of this whole domain. And so that is actually a cross section. You see on the inside, the tubes are smaller, so the magnetic field is stronger. Yeah. And yeah. Yeah, and as I told you, these curves really, these tubes follow geodesics of certain metric on this domain. Okay, so of course variational principles are really nice, yeah, and it turns out that this variations of such a configuration, yeah, can be formulated. They all come from diffeomorphisms. Yeah? So if I apply a diffeomorphism, yeah, to this magnetic domain, including the field lines, the integral curves of the magnetic field, yeah, whose density gives also the norm of the magnetic field, yeah, then that will be an admissible variation. So you can also say you treat this magnetic field as a differential form, a two-form, yeah, and then you push forward this two-form by a diffeomorphism, yeah, and that's how these are the admissible variations. Yeah. You can't just change your magnetic field at will. You just always have to make a diffeomorphism and apply it to the whole situation. Yeah. And and then the theorem is that if you have such a magnetic bubble configuration, which I call it, yeah, then this is in this magnetohydrostatic equilibrium if and only if it's critical under admissible variations of this energy. And the energy is the integral of over the magnetic domain, yeah, of this extended P. So, you know, that's a little bit it's interesting because there is no gas pressure inside. There's no gas inside of magnetic domain, but still P is what would be the gas pressure if there would be no bubble, yeah? And this actual norm B squared half of the magnetic field. That's the energy, and you vary this, yeah? And that is interesting because then you can just say, given such a, yeah, I model my bubble configuration by just curves, yeah, by let's say closed curves or like this, yeah, and that will give me a magnetic domain and a divergence-free vector field, yeah, just by the density of these curves. That would be at least a numerical approximation by finitely many curves, yeah, and then I can numerically try to minimize this energy and vary the curves until I get a minimum for this energy. Yeah? And that's how this comes about. Yeah? See, you just minimize, and then in the minimizing configuration, you know that will be a solution of this magnetohydrostatics equation. Okay, so yeah, this looks almost like topology. Yeah, see, let's try this on the Borromean ring. Yeah, and then
hello, Ulrich. All these actual mathematical models are available in the physics literature.
That's a combination of several models that are in the literature. So you see the assumption is really that you say it takes the limit, there's really no gas, where there's already little gas outside of these structures, these magnetic tubes. And you say there's no there's no magnetic field outside and so no gas inside, and they call it current sheet models, or if they don't have no gas, then they call it a force-free magnetic field model and so on. Yeah. They have all sorts of names for models, yeah, and that's on the line. That's just a combination of some ideas, but it's a model that as such hasn't been really done in the solar physics literature, yeah, but it's it's numerically very accessible, and you will see it really gives good results. So in the end, I will really compare it to actual solar pictures. Yeah. But right now, you see, it's just fun to say, I have these Borromean rings, and and at least on the outside, I have this constant thickness cubes, that makes the rings. Inside it will be more complicated. A trefoil knot. So this, of course, that's more interesting for us mathematicians than for the solar physicists. Maybe somebody gets an idea how to build a fusion reactor. I don't know. They also use this magnetohydrodynamics. But anyway, So that's what I said. So there was this reformulation that inside of this MB we have these geodesics. And let's talk about thin magnetic tubes now. So these are just these structures, maybe, like thin tubes around curves, but the thickness could be variable. So a good, let's say, this cross-sectional area A depends on S. And then we have this magnetic flux H. Which is just the norm of this magnetic field times the area, assuming that basically in the thin tube field goes parallel to the Soul curve. And then this energy we want to minimize can be written down like this. Integrate this.
The area is the area of the cross section. Oh yeah, right.
Yes, yeah. And then you say the energy is the integral of. Somebody has again to be muted. Okay. We have this integral, and you see, if we are only prescribing the curve gamma and do not care about which cross section, we should minimize over fixing this flux. No, it's. Do you still hear me?
Yeah, hello?
Yeah, okay.
Professor Kulkarni, you have to mute yourself.
Now
Unmute. Yeah.
Now it's great. Okay, and then, but if you then just minimize, point-wise, you minimize over this cross-section in order to get a minimal energy. And then again, you see the resulting energy, which now depends only on this curve gamma, will be again, the length of gamma in such a conformally changed metric. So, and the metric is square root of 2p times the Euclidean metric. And so, this is the minimization. So you start with any cross section, and then you minimize, so get minimal area, minimal energy, and then you get this length. Okay. Up to a factor of square root of 2, that's true, but it's for geodesics, it doesn't matter. But then that means a thin magnetic filament inside of gas-filled atmosphere will also follow geodesics of a conformally changed metric. Now this ds squared is just this pressure times this pressure function times ds squared. Okay, so we have to come up with a pressure function, and so that is something that has to be measured, because it also has to be, depends on the temperature of the atmosphere. But a good approximation to what's really going on our sun, yeah, is to say the pressure is norm, x is distance to the sun center, radius, yeah, radial coordinate to the minus lambda, where lambda is 23. Yeah. And so what you see below is geodesics with respect to this metric for different values of lambda. Yeah. And on the left, you see this interesting behavior that yeah, some of these geodesics are curved. Yeah, they start at the sun surface and go back to the sun surface. But some of these geodesics, yeah, are really, you go out to infinity and in fact come back. That's what you should think. Yeah. And in fact, these are really length minimizing geodesics between some point on the left and some corresponding symmetric point on the right. Yeah. So that's really length minimizing connections between points. Yeah. What you see here. And so what's going on here? What's going on is that if you look at a certain plane, you take a planar section of the whole thing, yeah, then on this plane, yeah, you can just take this power function, complex coordinate z goes to z to the 2 minus lambda half, so some power, yeah, and this will map this plane, yeah, yeah, also to the plane, but in fact the metric we have is really the pullback of the flat metric on this target plane. Yeah, so kind of that means the metric we have written down is really a flat metric, yeah, on each plane through the origin. Yeah. That doesn't mean it's really flat, because there's really some negative curvature on, let's say, horizontal planes. Yeah, but still, it's a nice.
The sun is supposed to be at the center, right? At the origin. Or
Yeah. Yeah, this sphere I have drawn is more or less the sun, and the center of the sun is really the origin. Yeah.
And what's lambda?
Minus lambda is 23.
Oh,
just some number. Yeah, you match lambda such that it best fits what can be measured, sort of. Yeah.
oh.
Yeah. It's different for different stars. Yeah, and it depends on the temperature and whatever. Yeah. Mm-hmm. Okay, and so what's going on now? You see, we have this branched cover, which really branches the complex plane onto itself. Yeah, or as 23 times covered or something like that. Yeah, and then if the total angle will be larger, like I know 23 times 2 pi, yeah, which is covered, and then if you look at this surface intrinsically, it looks like a cone, yeah, with some negative curvature hidden in the center of the cone. Yeah? But then if you really do length minimizing geodesics between points on the boundary, yeah, then for short distances you get these curved connections, but then very often, in the end, it's the shortest connection is going from the boundary of the cone to the center and going straight out again. Yeah. So that's and that is so it's not really a complete metric, of course, yeah, but it's yeah, as a metric space it's like this, and length minimizing geodesics have this behavior, and that is really interesting, because then you can, that's an explanation why you never see really loops on the sun that connect points which are very far away. Yeah? So it's only 1/23 of the solar perimeter. Yeah? That's the largest distance you can have for the solar loops. Okay, so let me then show you how really you can apply this to make images or movies of the sun. Yeah. So one possibility is that you start with a with the so-called magnetogram. That means you just measure the magnetic flux through the surface. Yeah? So that's a texture on the surface. Red means the magnetic field is coming out of the sun, and blue means magnetic field is going in. Yeah? And that is something that can be measured, and it's measured on a daily basis, several times a day. It's published by NASA also. These are available data. Yeah. Therefore, you can really test your algorithms on it. But let's say you make a movie, fly by of some strange distant star with your starship. Yeah, then you can also use a random generated magnetogram, yeah, or you design your magnetogram, yeah, artistically, whatever. Yeah. So you just start with basically such a flux density on the sphere. The only because it's by Stokes theorem or divergence theorem, yeah, you have to use as much blue as red, otherwise you don't get a magnetic field, yeah, with this boundary flux. Yeah. But yeah, that's but this is a starting point, yeah, and for numerical purposes, then you discretize it, you replace it by a finite collection of points whose density approximates this continuous flux density that you are given. Yeah? And yeah, that is, for example, magnetic flux as measured on certain date in 2011. Yeah? And that's the corresponding stippling that we get. Yeah? And then you see, you have to, then what we do is, then we know this energy. The energy is really the length. Yeah? And then that's really a combinatorial problem. Yeah? You have all these red points, yeah, and all these blue points, yeah, and we want to match them. Yeah? To each red point, there should be a corresponding blue point. Yeah? And we know the distance. We see there was an explicit formula for the geodesics, and so there's a simple formula for the distance in this metric. Yeah? And that is kind of a cost function for this matching. Yeah? And then there is a combinatorial algorithm for this assignment problem, yeah? Which also runs quite efficiently if you do it on a computer. Yeah? So that's really an optimal matching between red and blue points. Yeah? And you see, so sometimes the matching says you should go through infinity. That's where you have to see these straight lines. Yeah? And going out and coming, it doesn't really matter where they come back. Yeah? And you see these arcs. Yeah? So that would be really a solution in the limit if you have a really high gas pressure, which really makes very thin, compresses really thin filaments. Yeah? So that's what you're looking at, is kind of a limiting case also of a real solution to this problem that we want. Yeah? But then what we this gas pressure is really not really infinite, but moderate. Yeah, and so we then look at the same thing for moderate pressure, or increase the magnetic field. That's equivalent. Yeah, and yeah. Oh, wait a minute. No, and then you get different curves. Yeah? So this comes about by numerically minimizing this energy, but starting with this initial configuration. So the foot point matching is already fixed. So the whole topology is fixed. Yeah? And there's no linking and knotting going on because of any energy minimization, sort of. Yeah. And then you optimize the shape numerically. Yeah. And so that's what's going on. These thin tubes really become thicker tubes, you know? And yeah, and then you are almost done. You just come up with a good method, physically based on how much glow you see, yeah? And then you can render your sun, yeah, based on these curves, yeah? And you see, this is really this photo of the sun at the same time. Yeah, so and it's roughly comparable. Huh? Yeah, so that's side by side. You see the two. Yeah, this from this October day in 2011. Okay, and that's in fact from a random magnetogram. Yeah. Yeah, that's a magnetogram that is artificially generated. Then you do this matching and optimizing. Then you have these curves. Yeah, that's just how you. Yeah, and then you put some texture on the surface so that it looks even better. It was just to show that it's really applicable to science fiction movies, you see. Yeah. Okay, then there are also, in reality, there's also some twisting going on, and that has to do with the sun surface is also moving, and then you can have some rotation on the surface, and then these loops get twisted, yeah, and they that's interesting for several reasons for solar physicists, yeah. But we can also do this, you see, we just minimize energy and we just, yeah. And you see, if you twist, then really these things go up and open up. And that's an interesting model for coronal mass ejection. Yeah, so that's some solar flares. Yeah. That's a model for how they work. Yeah, this is. If you render them, yeah, that's. Okay, and you see, that's just another demonstration how useful this might be for making movies, yeah, because that was kind of the audience, that's the audience where we present this in this computer graphics community. Yeah. But you see, there's some really interesting differential geometry in the background. Yeah, there's some conformal changed metrics in the neighborhood of the sun, yeah, and some geodesics and so on. Okay, so that's the end of my talk. So thank you, and you can find both the paper and also these videos also at this web address. It's a project page of this talk. So then, yeah, thank you.
Okay, so let's thank the speaker. So is there any questions, comments?
I have a question, please.
Yeah, please.
Ulrich, first of all, thank you very much for very interesting lecture, very expressive picture, very nice mathematics. My questions maybe will be very stupid, but at least for many years I'm trying to find the answer. This is related with geometry, with hyperbolic geometry. Let's suppose that we have just a figure 8 knot inside of three-dimensional sphere, okay? Classical situation.
Yes.
Then outside of this figure 8 knot, we can introduce Riemannian metric of constant curvature, say -1. There are many such metrics, but at least exactly one of them is complete Riemannian matrix of constant curvature. So we have a hyperbolic structure, complete hyperbolic structure outside of figure 8 knot. It's understandable, huh? This is classical from Thurston lecture, and indeed first was obtained a bit before Thurston by Robert Riley. But question is the following. Suppose that we already got this hyperbolic structure outside of the figure 8 knot. Could we put some kind of magnetic field in such a way that the magnetic field exactly describe the geometry of this hyperbolic space?
Yeah, that's it's an interesting question. So one other physics application is that you have a if you have a knot, let's say, you can also have this fluid motion, which is basically a potential harmonic field. You interpret this knot as a vortex ring in some fluid, and then in fact the velocity goes to infinity, if you approach the knot, back like 1 over distance from the knot, and that then you could also use this to introduce a metric. I'm not sure, or probably depends on the geometry of the knot. It doesn't have constant curvature, but probably it has some kind of negative curvature. I don't know.
Yeah, no, the reason is that this hyperbolic structure is very canonical, is unique, more or less. So it's supposed to be also unique and canonical magnetical field related with this structure. Because I'm not expert in physics, maybe this is a stupid question.
Yeah, yeah, that's right. But that means, since probably whatever metric you do physically also depends on the geometry really of the knot, of the figure 8 knot, and if you can manage to get some canonical Riemannian geometry like hyperbolic or so, that also means you have found a canonical shape for your figure 8 knot, which also would be very interesting. See, yeah, that's probably why you got inspired by these pictures, because you find some optimal shapes for these knots.
Beautiful picture like yours, yeah. But still canonical form is not okay, thank you very much.
Okay, so any more? So any more questions?
Is the conformal change of the metric a mathematical convenience, or has it any other physical justification?
No way. These were theorems, you see. Here. So if you have let's say let's forget about the gas. Yeah, if you have a magnetic field, yeah, and this nabla BB equation you can also rewrite as curl B cross B is 0. So curl B is proportional to B. They call it a force-free field or Beltrami field or whatever. Yeah. And a special case would be just look at the gradient of a harmonic function. Yeah, that would be curl B is 0. Yeah. Then it's really a theorem, yeah, that the field lines of such a vector field are geodesics with respect to this conformally changed metric. Yeah.
But that conformal factor e to the minus 2u, that u, does it have some, can it be physically calculated or some physical calculation?
Yes, yeah, there were two results of this type. Yeah, wait a minute, there was what? Yeah, here, see? That is just the norm of the magnetic field. Yeah? If you have this equation, for magnetic fields satisfying this equation, the field lines are geodesics of this metric. Yeah? Nice. That was one case, and the other case was that you have this here. Yeah, see that you have this gas. Yeah, you have this atmosphere, which is let's say you have no magnetic field. Yeah, just gas. Yeah, with some pressure function. Yeah, could be anything. Could be e to the minus height or whatever, like barometric formula, or it could be any pressure function. Yeah? But you have only gas, and then you imagine what shape does a thin magnetic tube, yeah, inside of this ambient gas. Yeah? So vacuum tube filled with magnetic field. Yeah? What shape would it take? Yeah? And the answer is it's a geodesic with respect to this metric, yeah, and the conformal factor is really this gas pressure. Yeah? The conformal factor is given, and also the fact that, yeah, and also the fact that there is a conformal factor, that it's conformally flat, is also comes out of the physics. Yeah?
How do you draw these pictures?
Well, I think we using the same software that also is used for, is the main software used for doing professional movies and special effects. Also, that's called Houdini. Yeah? And the advantage is that, first of all, it comes with a free version that can do everything, also more or less. So you don't You can give it to students also, and it's really free, yeah, unlike Mathematica or something like that, even, yeah. And it's very professional because and very optimized because everybody, all these professionals use it, so it has to be good. And also, you can do all the computations inside. Yeah, see, it's not just for picture making, yeah, but you can have this graphical programming and different languages, and it's very optimized also. Yeah, so a very efficient way, programming environment, and you can see if you want to make things like that, you want to do some programming and some parameter changes, and this a little bit thicker and something. You need a user interface. You need a lot. Yeah, it's not just writing some C++ program or whatever, and then you have something. Yeah, and yeah, so we are quite happy with this Houdini kind of software. That's for, I think, for mathematics.
Houdini.
It's very
What is the name?
What's the name of the software?
The software is called Houdini. Yeah, and
Houdini.
Houdini. I like this magician. Yeah, and you see yes, a side fx on the bottom right. Yeah, that is really the company sort of. Yeah. And they gave us some free, some full licenses also. That's why they
Can you write it or can you spell it?
Oh yeah, yeah.
Maybe write in chat.
You see it in the chat?
Not yet.
Mm-hmm.
You wrote somewhere else.
No.
Oh, is it in the chat? No, no, this is
In the chat, yeah.
it's something else.
No, in the chat it is not visible yet.
That's interesting.
Maybe you can send me by email
Yeah.
slides and the name of the software, and I can sort of, I can.
But it must be visible because I see all the other messages.
I see it. I don't know. I don't see it here yet. Maybe there is some internet issue. Or I don't know. Maybe chat is blocked or something.
No, wait a minute. No. That is only to. I send it only to Mukudmani.
Now we can
Now
see.
it is.
Yeah.
Now it's to everyone. Okay.
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 The magician.
Okay. Yeah. So just 1 minute. So I think it was an interesting talk, and we thank the speaker again. Okay. So I will have to leave now. So